Today's talk is this two highlighted words, robust and long-term. Those are the two keywords that I want to introduce throughout this talk. So I'm a SLAM guy, and I do use a lot of different perceptual sensors like that to navigate through the environment. And you probably have seen many talks here talking about the challenges that we have, including all the perceptual challenges. That's better. Thank you. So you probably have seen many talks about this appearance changes we have to face, day to night shift, illumination changes, weather changes, that kind of thing, perceptual variation. But another thing, if we go for long term, what we have to think about is something else, like structural change. It might be somewhat philosophical statement that things change and nothing lasts forever. Yeah, right. Things appear, things disappear. And if a robot wants to navigate through the environment and do the mapping for a long time, year, 10 years, 30 years, we have to somehow handle this change properly, right? So those two are the main key interest of mine when doing research. And I want to share some of the motivation that I had during my research experience. So what I'm showing you is the case that we were in the utility tunnel. This is in 15 meters down ground. It transmits the power to the city. And as you see, it's very dark. It's natural that you don't see anything because it's very dark environment. And due to this situation, we cannot rely on an RGB camera at all. LiDAR works here, fortunately. So we were using the LiDAR at the time. Dark tunnel inspection, yes, we have to search alternative solution other than RGB camera. And in this project, when we were doing this kind of drone-based search and rescue in a fired house, and we mimic the situation by using an artificial fog machine, we fill the indoor place with this thick fog. And what you're seeing on the right is what LiDAR sees from this thick fog. So it sees all the ghost effect coming from this fog, and that's totally not good for the robot. I'm not just saying this specific case. This can happen in our everyday life. We might have a fog day, rainy, stormy night. We have to drive, and autonomous car has to drive, and robot has to deliver, even in this weather. So those will be some perceptual challenges that we have, and the structural challenge that I mentioned. This is the map of Pangyo, a small town in South Korea, and it's a very populated town. You see it's empty because we went there at 4 a.m. in the morning. That's why you see so many cars and not many pedestrians. But what I want to say is if I go back there now, there will be different cars, different pedestrians. Things has been changed. And if you want to do matching, if you wanted to localize, navigate through, you have to distinguish what is a dynamic object and what is the ephemeral and what is something permanent, is something that I have to rely on, right? So kind of summarizing, those were the kind of motivating experience that I had. And that's the time that when I turned my interest to how can I solve this problem? So here I want to introduce my strategies, something that we did from our lab. First, if we were to use camera and LiDAR, what we can do. This is the corridor in the department. And you can think of this one as a patrolling robot at nighttime. There is a sensor-induced light. When you enter the corridor, it detects you or robot and turn on the light. What human does in that kind of situation is our pupil adjusts rapidly to the light reaction, right? So my question was, can we do that exposure control good enough so that we can obtain the best quality image from the beginning without going through the pre-processing? Let's grab, acquisite the best image. That might be the first step, I think we can go. So we thought about that. So we developed some camera control. Even if we control the camera and always getting the best image so far, we still need to expand that further, right? So the next thing that we did is let's try to see what's the better representation for the RGB images. What's the better representation? What's the best description to encode a place for camera and LiDAR? So those are some of the things that we tackled in the camera and LiDAR point of view, but that was not enough, like because of the situation that I mentioned earlier. So we tried to seek alternative sensing, and what we found is there's a beyond spectrum sensors like radar or thermal long wavelengths IR cameras. So that could be really nice alternative, but there are not many people working on that. I know there's an emerging community who's working on the radar SLAM or thermal SLAM. I really loved it. But so far, compared to the popularity in the LiDAR or camera, this is somewhat overlooked, I think. So there's a really big potential. And the last topic that I want to say is the structural thing that I was mentioning. So how can we detect changes? And if we know what the changing part is, can we update the map, maintain the map in a long-term manner? So that's the last topic in this talk. Okay, so start with the camera and LiDAR. So like I said, what we tried at the beginning is let's grab the best image from the beginning before even starting the pre-processing at all. You can think about this problem as it is. If you apply very low exposure time, if you only open your pupil very short period of time, what you can get is the image like A, it's very dark. If you open the camera aperture for long, if you assign a long exposure time, what you're gonna get is something like E. What we want is somewhere in between A and E. If only we can measure the image information level as a number, we can plot like that, having a y-axis as the image information level and x-axis as the exposure time. And this problem is nothing but an optimization problem to find the optimal value of C, exposure time, that yields the best quality image, right? There are two things that we have to think. First, this image quality should good for robot. So, which means we have to have a lot of gradient because robot loves gradients in the image. And we need to minimize the saturated portion of the image. So we combine those two together to develop a metric. So metric is ready. Another problem is each function evaluation in that function corresponds to the actual acquisition of an image, right? If you want to evaluate the function at the larger, longer exposure time, you have to open up the exposure aperture for a long period of time. So each one of this function evaluation is very expensive. So for solution for that, Bayesian optimization is a perfect solution when your underlying function is unknown and your function evaluation is very expensive. This is very good because it allows you to reach to the optimal value in a couple of steps. And we did some other tricks, but you can find it from our paper. But this allowed us to complete our camera exposure control. What we did is we mounted 3 different cameras running in the different exposure setting. On the right, this is manual, which means fixed exposure time. And obviously it fails right away when you enter the bright scene, right? Quite expected. What we really wanted to do was to outperform the auto exposure on the top left, auto exposure developed by the camera manufacturer software. We want to have this camera controller better to focus on the underlying structure, extract more gradient, and fast enough to be implemented for the real-time visual SLAM. So that's what it is. So using this, we can obtain a best image, but still, we have to, the next step is to think about the representation, how we can develop a descriptor for the RGB camera and, and LiDAR. I know there are de facto standard practice. What we do in the robotics is use a feature point in an image as a word in a document, right? The bag of words and a kind of thing. So that means if a point is a word, a line in an image would be a sentence. Then the line-to-line matching between images will be sentence-to-sentence matching in the documentation. There are many things, tons of work, research on that topic in the natural language processing community, translation, shortened sentence matching. So we can apply those techniques into it, and assuming the line as a visual sentence. And the result is quite amazing. We freeze the first scene, and we are entering into the scene depth. As you see, which means you have a large scale drift. But as you see, we were able to make a lot of matches. And here I'm showing you only the line, but line could be a really perfect alternative with the points. If you combine points plus line, your performance will be improved. So what we are heading for is combining the line and the points for the better description and matching. So that was for the RGB images. And what about the LiDAR? So one of the things that we thought about the LiDAR, the problem is it's very heavy in terms of memory size, 100 megabytes, easily gigabytes. How can we encode a space written in the point cloud in more compact manner? So what we developed is called scan context. What we did is from that polar view, we are stacking each slice as a column of the descriptor. And x-axis would be the azimuth and y-axis would be the range from you. So it's an egocentric descriptor. What this descriptor is showing you is actually it's a skyline contour around you, because each one of these pixels indicates the height of the building. So you're looking at the skyline around you, and we assume that this should be enough feature for us to recognize for the localization. So we applied that to Kitty, see if that's true. So this is 2 Kitty data set. In Kitty, one time, the upper scan context indicate the first visit, and the second visit in a different timestamp, they revisited, and as you see, they are very similar. Only difference is the column shift. Because the x-axis is the azimuth value, the column shift, what it indicates is, it was a situation like this. In the first visit, the robot vehicle was coming into this direction, the azimuth changed. So in the second revisit, it was approaching to the same intersection in a different angle. So if we can only shift the column and match, we were able to match this one and making this rotation invariant descriptor. And as you see, this is 60 by 20. It's really compact. Think about this, how compact it is compared to the actual point cloud of the site. And what's better is we can do a reverse route localization. It's easy. If you wanted to make the reverse route, you can take the half of the scan context and put it on the other side. And that's exactly depicts how you're going to see the scan context when you are coming into the same spot at 180-degree shift. So we were happy for that, and we realized this format is just an image-like format, two-dimensional. So what we tried is see if we can apply this one into the long term. So there's a NCLT data set by University of Michigan. They collect the data throughout the year, monthly taking the data set. And what they did is listed like this. So what we tried is, okay, let's make a very simple CNN, and let's make it memorize about this town and see if it can localize throughout the year by only training using a single day data. The result is quite promising. You see the PR curves drops, obviously, just because we didn't train further, but it shows the potential of this long-term localization capability. And only if we retrain this one in every other 3 months or 4 months, we would have done things a lot better. So, so these topics are something that we tried for the camera and LiDAR, but because of the situation and the demos that I showed you earlier in the video, it was not enough. So we had to find alternative solution rather than camera and LiDAR. And then I come to know this radar and thermal related works. And there was luckily one professor, Professor Martin Adams from Chile, visited South Korea, and he showed me a lot of works in the radar. And that's when I was flying the drone in the fogged indoor, I was frustrated to see the LiDAR is failing. And yeah, I thought that, yeah, maybe this could be a solution for my problem. So our group dig into this issue, seeing what's the alternative sensing beyond the visible spectrum. Let's go to the IR, let's go to the radar. And there's two different popular radar in robotics. One is the spinning radar by Navtech, and the other one is by TI, radar on chip. But the problem of this radar is that you see it's very sparse, and there's a lot of noises happening. This is something that we have to overcome to earn the robustness in the sensing capability. What about this thermal camera? It stopped, but as you see from even in a single snapshot, thermal camera is much more not colorful as the RGB is. There's not many variation, and also the noise level is high, so you have to overcome that too. So I want to introduce a couple of our works on that. So we combined LiDAR with thermal camera. The main purpose of that is to run this SLAM algorithm in a complete darkness. So this is the result. As you see, left and right, day and night, but thermal camera doesn't care if it is day or night at all. The thumbnail on the right shows the RGB images stream coming from the night scene, but see how the thermal camera works, that doesn't care. You see the color difference a little bit just because each one of this point color indicates the temperature. So nighttime, it was a little bit colder. You see a little bit more blue, close to the 0 degree. But other than that, it perfectly captures the mapping, the environment nicely, and it's a SLAM. So when it is coming back to the previous location, it makes it look closer and doing things. And another thing is that after all of this thing, what you're gonna get is not the colored point cloud, like we are all familiar with. It is, the point is associated with the temperature. So thermographic point cloud is something that we get. And this is quite meaningful for many inspection application, because sometimes the temperature distribution of the environment kind of help you what's going on beyond what you're seeing. We have two thermal camera related works in this IROS. Unfortunately, you missed the first one on Monday, but luckily you still have a chance to check out our second paper, which is going to be at the 4 p.m. today. So if you are interested in, come and visit us. We'll be happy to talk about more about the SLAMs using thermal cameras or IR sensors. Got a quick advertisement. And for radar, so we tackled two different radar types. One was the spinning radar. As you see, it has many noise level and sparse. Well, we thought the computer vision community use a phase correlation for those kind of noisy images. So we apply that to see if we can estimate the relative motion between those two. And as you see on the bottom, it's working fine. It's a 2020 ICRA. After that, tons of nice work came out. You probably can see radar is really performing nicely and showing a lot of promising result. And another radar by the TI, the nice thing about this one is this also gives you the velocity, not only the range. So additional velocity information is really meaningful, because what we propose is this kind of unique configuration, orthogonal configuration, and we can combine this velocity information in a 3-dimensional space and complete the 3D linear velocity. And plus, if you plug in the IMU and integrate that over, what we can get is a 1/6 of full linear and angular velocity. And if this linear and angular velocity is correct, accurate, we should be able to draw the time integrated odometry and see if that works. So we did we applied that into that foggy environment. And okay. And the upper row is from the LiDAR. We were just running a typical LiDAR odometry. And unfortunately, because of due to the high level of the fog, it failed. But if you see the bottom row, radar doesn't care about this. If it is foggy, rainy, and as you see in let me go to the previous slide. So this is in the box. You totally encapsulate in the plastic box. You can see through the plastic, which is cool. So can we run the LiDAR-based robot in a typhoon, monsoon? Can we? So we think the radar has a lot of potential. So we really like it. if you are in the SLAM person, why are you all doing the direct method? I don't know. My students really love the direct method, but there are tons of other works in the feature-based, which also works really nicely on the thermal and radar. So don't be biased. Anyway, that's the alternative sensing. And I think I want to move on to the very last topic of how we can handle the structural changes. It's not just for a long term. Actually, it is happening in a very short period of time. For example, it was the case that we collect the data. As you see, there's a many shadow effect happening because the car was passing with a LiDAR on. There was a bus next to you. Beyond the bus is a shadow, which means the LiDAR couldn't return, and it's totally empty space. If you wanted to fill that space, the empty space, you have to return, U-turn and come back, right? But at the time, the other side will have some shadows, right? To make the complete map, you have to merge two different maps. And when you're comparing two different maps, there will be many buses, cars are different. So you have to know what's the difference to merge the map and maintain the structural information. That's the key idea. And even shorter period of time, what you're going to encounter is something like this. This is from the KT dataset map and 3D map. There's a repeated pattern happening. If you zoom out, pop out the associated image for that, there's a bicycle. So that's the case when car was moving and there's a bicycle right next to you, moving in the same velocity with you. So it was captured over and over and over again, having this repeated pattern. So this is ghost effect, ghost pattern, right? So it should be removed. How can we remove? So it's the same question, map to map comparison, scan to scan comparison. Basically, this is a point cloud to point cloud comparison, right? What we think is so here's a map 1 and map 2. Can we compare if something lingers, static, something was there, it's not, then it should be dynamic. But it's not straightforward like that because every map has some level of uncertainty. Nothing is super accurate. Even if it is super accurate map, you will have 1 centimeter, I don't know, 2 centimeters. You can't avoid errors in the map. So direct naive comparison wouldn't work. So this problem is comparing two different point cloud under estimation error or estimation uncertainty. Our idea is to differ the resolution of the range image having a final level and remove all the object, all the difference from the final level and put it back at the coarser level. So we name this one as a remove then revert. How this one works is let's remove 1, 2, 3, couple of steps, remove everything in a final level, and then revert it back. So as a result, what you're going to get is something like this. You might have seen this video playing. So we have a first map in the blue. And we came back to a couple of months later, which is in yellow. We aligned those using a multi-session. It looks well aligned, but if you zoom in, there's a slight difference. And if we plot the difference with a red color, you're going to see the changes are happening at the tip of the trees, cars, pedestrians. Those are the changes, as you see. But now we can compare the difference, which means now we can plot only the difference on the map, and we can remove those out of map, making empty. Seeing this kind of empty city is not realistic. You can't get the empty map, totally empty map at all. But we can do that. And handling this difference is very useful because now this can be further combined into the map maintenance. Now you have a delta map, so positive delta map, negative delta map. Many of you are familiar with GitHub, right? SVN, the version control. They show you the deltas. If you want to go roll back to 1 year ago map, you can apply this thing. And the size of the maintenance is the delta map. So think about how compact that can be compared to the handling the large size point cloud. Okay, I think I'm toward the final slide. So what I want to say as a concluding remark is we had a chance to run our sensor system inside the Seoul city. It's a metropolitan, it's very populated, but government blocked the several blocks for us. Only us was running into this in the middle of the city, and traffic light was totally controlled. It was 5 a.m. in Sunday morning. That's why you see very uniform illumination. As a developer, all students in robotics, they want this kind of environment. No illumination change. There's no dynamic object. We are the only one. Look closer perfectly makes. Uniform illumination, no dynamic object would be ideal, but that's not the real world story. What's real? The same spot after 4 hours when the block is over, it stopped. Yeah, okay. So you see a lot of cars. Sun rose, and then you see illumination changes, shadows happening, cars, pedestrian. So there's many dynamic objects. Extreme weather might be happening. Long-term changes are occurring. So we have to overcome these real challenges happening in the real world. So I think I didn't really tell you much about the deep learning in this talk, but I believe nice combination between the deep learning adaptation of some learning method into the model-based approach would be a nice solution for that. And also, like I introduced, complementary sensor combination beyond the camera and LiDAR, maybe camera plus radar, camera plus thermal, LiDAR plus radar, something like that could be a solution for this. So that was the end of my talk, and it was supported by many different institutes and companies, and we had a really nice, great collaborators. And I would like to thank all of you for the attention.
We have time for some question. So please, came at microphone. Any question?
So we have the main authors of most of the papers here in this room. So detailed question could be asked to them also.
Yeah, I have a question. I mean, it's something like related to the starting point of the presentation, the exposure problem. So what's the performance of the system in terms of time needed to decide the right exposure? And I guess you work only on aperture.
Right. So that's the detailed part, but
please.
So that's the detailed part. So we, as a very beginning control, we have to do the batch. So it takes longer. But after that, we also measure the illumination variance. If it starts, you just run the batch. That will take longer time than the others. But still, even the batch, you saw it converts within 5 steps, which was not too bad. It supports 30 hertz. Sufficiently.
And what about using perhaps changing ISO sensitivity behind using only the aperture?
Oh, I didn't. Yeah, actually, for the visibility, I'm showing you the exposure versus the information level, but actually I am controlling gain and the exposure. It's a 2-dimensional Bayesian optimization. Yeah, that's a good question, because otherwise you have a lot of noise produced by the IS. Yeah.
This is also what happens in cameras.
Yes, correct.
Any question?
I thought the delta means of in terms of compression of finding only the delta and archiving that was pretty ingenious in terms of approaching that from a mapping perspective. Do you have any future work of where you think you'll go next with that approach?
Well, that was like conceptual thing that we published in the ICRA. We haven't really go farther than that, but as you indicate, I think the map maintenance, because now it's a lot of robots are going everywhere, they are collecting a lot of maps. So I think the next step will be developing that kind of map encoding, comparison, updating. I don't have any specific direction for that yet, but I see a lot of different potentials from it.
Thank you.
Thank you.
Well, thanks for a nice speech. I was curious about, you said detecting a dynamic point was comparing a map between 2 timestamps in a long period of time. And do you have any advices about the algorithm for detecting such a dynamic point? Because I tried some kind of a neighboring algorithm like that, but it took a really lot of time.
Comparing, making the difference map.
Yeah, detecting a map difference in the map.
So what we did is based upon the range image. So from the point cloud, you generate the range image, but what you can do is you can differ the resolution of the range image in T and T-1 scan. When you're comparing those, difference at the different resolution, just like an image pyramid you can think of. So you have many pyramid level, and the step 1, 2, 3 are all differing the resolution of those two.
Thank you.
Thank you very much.